Hello, my fellow math magicians. Today I'm going to be talking about finding limits graphically and finding them numerically. This is section 1.2 of the textbook that I have that I'm using as a guide. And we have our initial function here, f of x, and it's equal to x cubed minus 1 over x minus 1. So we have our graph here, and we can see that it has a hole right here where x is 1. That is because if we plug in 1 for x here, well, let's see, we get 1 cubed, which is 1, minus 1 is 0, and then we get 1 minus 1, which is 0 again, and we get 0 over 0. We can see that it gets closer and closer to some number here on the y-axis. We just don't know what number that is. So if we plot these numbers here on our x into our f of x, we will see that it starts to get closer and closer to some y value. So we have here, for some x values, 0.75, and we get the value of 2.313, and we got 0.9, and we get the value of 2.710, and so on and so on. So we're approaching it from underneath, which would be from this side right here, our left-hand side. We're also coming down from the top, or the right-hand side, approaching that hole. And as we can see, these values also look like they're approaching some number. We got 2.3, 2.7, 2.9, 2.997, and then we got some undefined value for 1. Well, we got 3.003, 3.030, and 3.310. If you plug these numbers into your calculator, you should get similar or the exact same values. So what we can assume about this function is the limit as our x approaches the value of 1, we get the value of 3. We can write this as the limit as x approaches 1 of our f of x is equal to 3. Our f of x being this function up here. So this leads us to the informal definition of a limit. If f of x becomes arbitrarily close to some number L, as x becomes arbitrarily close to some c, then this can be written as the following. Limit as x approaches c of f of x is equal to our L. Now we have our second example, and we are trying to figure out the limit as x approaches 0 of this f of x right here. Our f of x being x over the square root of x plus 1 minus 1. And as you can see, the reason why we would need a limit to discuss what happens at 0 is because if we were to plug in 0, we would get 0 over the square root of 0 plus 1, which is 1, minus 1, which would total 0 over 0. Thus, a hole is created in our graph. So the way that we're going to be finding this limit is by pretty much using our calculators, where we plug in very small values close to 0, but not 0, and seeing what happens as we get super close to 0. For example, negative 0.01 gives us a value of 1.99499. As you can see, these numbers get really close to 2, but we'll never actually get to 2 because we can't plug in 0. Again, from this side, the positive side, we are getting really close to 2, but not actually at 2. The negative values of x we have plugged in evaluate to this left-hand side approaching this hole. The positive values that are getting smaller are approaching from the right-hand side. That is just something to note for later. So here we have an example where we're supposed to find the limit of our function as x approaches 2. F of x is equal to 1 when x is not equal to 2, and 0 when x is equal to 2. If x is equal to 2, that value is 0. So here our x is 2 and our y is 0. Anything that is not 2 will evaluate to 1, hence our hole. Now the limit as x approaches 2 is actually 1. the fact that the function gives the value of 2 at 0 has no bearing on the limit whatsoever. The reason being is that from the left-hand side and the right-hand side, you are approaching this number right here, which is 1. We will also be talking about limits that don't exist, and there are 3 different types. There are limits which their behavior is different on the left-hand side than the right-hand side. There are limits that are unbounded or that go to infinity, and there is oscillating behavior. I will show you an example of each of those. Here is an example when the behavior on the left-hand side is different from the right-hand side. So this is the limit as x approaches 0 of our f of x, the absolute value of x, over x. Say we were to plug in 1. 1 over 1 is just 1. If we plugged in 2, 2 over 2 is just 1. So we get this constant line going across this side. But if we were to plug in negative numbers, say negative 1, we get negative 1, or the absolute value of negative 1 is equal to 1 over negative 1, which would be negative 1. So this left-hand side, or the negative values of x, will give us negative 1, and the positive values will give us a positive 1. Therefore, the limit does not exist because they do not approach the same number from the right-hand side and the left-hand side. Regardless of how big or small the numbers you use are, the behavior will be the same. You will get negative values for the negative side and positive values for the positive side of that function. This is an example of unbounded behavior. What that means is that the limit tends to infinity. If you were to put really small values in for x, you would see that the number that you get gets bigger and bigger and bigger the closer you get to 0. What you can see here is that they are both approaching positive infinity in the y direction. So you could say that the limit as x approaches 0 of this function is equal to infinity. But that does not mean that the limit exists. Here is an example of oscillating behavior. If we take the limit as x approaches 0 of sine of 1 over x, we will not get a certain value. As we plug in smaller and smaller values for sine of x, or sine of 1 over x, we will see that the values go from 1 to negative 1 to 1 to negative 1 to 1 to negative 1, no matter how small these values get. Therefore, we cannot conclude numerically that this will approach any certain limit. That's it for this video. In the next video, I will be teaching you guys the formal definition of a limit. I wanted to put it in this video, but it might be a little long-winded if I do put it in here, and the concept of the formal definition of a limit is a little more complicated than what we just did, where you would just plug in numbers and see how close you can get to a certain number the smaller you get. So I will leave that for an entirely different video. It is still technically chapter 1.2, but it's better if I make a whole separate video for that. Alright, if you guys like this video, give it a like and think about subscribing. Alright, thanks.